Okay, good morning. Let's get started. So first of all, a few announcements. The first one is that for today's meeting, it will be two parts. In the first half, I'll give a regular lecture, and in the second half, it would be our midterm test. So the midterm test will start at around 10:50 for us to deliver the papers, and it's about an hour and 20 minutes. So I have roughly an hour and 15 minutes for the first half of the lecture. So that's one thing. Another thing is today we'll start chapter 5 on association analysis and some reading assignment. It's from page 357 to 405 in the textbook. This is about 49 pages. And so that's the second announcement. The third announcement is we have assignment number 2 to be posted shortly today on Moodle. And the deadline, the due date, it's November 27. So you have almost a whole month to work on it. We are trying to release the assignment as early as possible, so it make it easier for you to schedule your time, right? So yeah, you have quite an amount of time to work on the assignment. All right, so that's some of the announcements I would like to make. Okay, so let's start our discussions on chapter 5 on association analysis. So here is an overview of the contents of this chapter. We'll give a definition of the problem of association rule mining, and then we'll discuss a very popular algorithm for discovering association rules from market basket data sets. This is called the a priori algorithm. And then we will discuss how, some of the efficiencies issues of the a priori algorithm. And in particular, we'll discuss introduce a few techniques briefly on how the a priori algorithms can be made more efficient. And finally, we will talk about some compact representations of the mining results. So typically in a association rule mining exercise, the algorithm such as a priori will have to discover what we call frequent patterns from the data. And in a typical exercise, usually the algorithm would be discovering or extract a huge amount of those frequent patterns. Sometimes the volumes is too big, that is hard to handle. And so there is certain way of compacting or compressing the mining results. So we'll talk about this compact representations of the mining results briefly at the end of this chapter. All right. So here it's the introductions of market basket analysis. The principal applications of association rules, which is something that we have previously mentioned before, it's market basket analysis. And it models supermarket data and discover association between different products or items, right, that are bought together, by customers. For example, these are some example rules that you might be able to discover from a supermarket data sets, such as bread implies milk, diaper implies beer, onion dip and salsa sauce implies a tortilla chip, etc. So you could be able to discover huge numbers of such association rules. And for each association rule, there are two components. We have the antecedent, which is kind of like the left part of the rule, and we also have the consequent part. So either the antecedent or the consequence, it's as you can see here, is a collection of items. So the semantics of an association rule looks like this one, means that if the antecedent, these items that are mentioned in the antecedents of the rule occur in a transaction, then it is very likely that the items that are mentioned in the consequence of the rule also occur in the same transaction. So that's the semantics. All right. And well, we'll consider a market basket data set as a collections of transactions, or what we call transactional record. Now, one more time, please don't confuse this word transactions with transactions in transaction processing, right? So previously we mentioned that in a typical transaction processing system, a transaction is like a process that you execute, which would access, a certain small amount of data in your data set. For example, you go to the bank and deposit a certain amount of money into your bank account. That is a transaction processing transactions. All right. So that transactions is an execution of a certain process, which kind of like increase the balance of your bank account by a certain amount that you deposited. Right. However, in the context of association rule mining or association analysis here, or market baskets analysis, the word transactions here means a collection of items that were bought together by a customer. All right, so don't confuse these two terms. All right, so sometimes we'll just call it transactional record. We put the focus on the word record here to distinguish it from a process, in transaction processing. So for our data model, each transactional record is represented by a set of items, such as milk, bread, detergents, rice, etc., etc. Now, in our context, we also call a set of items an item set, for short. This is a term that's typically used in the literature. Right? Now, notice that in our discussions, at least for this chapter, we focus on binary association rules, mining. That is to say, the rules that we're going to discover will look something like this. So in terms of the antecedent or the consequences, they're just set of items. There is no mentioning about the quantities of the products or items that is being bought by the customer. We only care about the presence or absence of certain items in either the antecedent or in the consequence parts of the rule. So again, one more time, we focus on binary association rule, which only care about the presence and absence of items. The quantity of each item's bought in the transactions is not considered in this model. Now, later on, we will briefly mention a couple of other model of association analysis, such as the quantitative association rule, and also a high utility rules. All right. So these will be briefly mentioned later in this course, in this chapter or in the next chapter. So for quantitative association, for example, in that case, we consider the amount of the items that is also bought as well. But we will talk about that later. Okay. So there are these other models. All right. Now, to facilitate our discussions, let us first define some notation. Let us use D to represent a data set, which is a collection of transactions or transactional records. And let me use I to represent the set of all items that are being carried by supermarkets. So for example, if the supermarket sell 1,000 different products, then the set I would be a set of those 1,000 items, right? So this is the set of all the items considering all the products. And let me use N to represent the total numbers of transactions in the data sets. And let me use T to represent a particular transactions in the data sets. Let me use ABC, either capital letter or lowercase letter, to represent each of an item. And we also use X, Y, Z, these letters to represent item set or set of items. Now, notice that every transaction, as we have previously mentioned, is just a collection of the items that were bought by a particular customer. And therefore, every transaction in a data set is considered an item set, right? It's just a set of items, right? Some more definition. So given a non-empty item set X, we say that a transaction T in the data set D contains the item set X if and only if the item set X is a subset of the transactions. That is to say, all the items that are mentioned in the item set X are present in the transactions. In this case, we say that the transaction supports or the transaction contains the item set X. All right. Now, the support count of an item set X, which is denoted by this notation, SUPX or sub X, is the number of transactions in the data set D that contains the item set X. So we count how many transactions in the data set contains X, all right? And that's the support count of the item set X. And if an item set X contains K items, we call the item set X a K item set, right? So for example, if X contains 3 items, then X is a 3 item set, right? Now, here in our notation, we use SUP or sub X to represent the support count of the item set X, right? In the textbook, it uses a slightly different notation. In the textbook, this is written as sigma X, all right? And in the textbook, it also uses the notation XX. This denotes the support of the item set X expressed as a fraction of the size of the data set. So in the textbook, it is defined as this, all right? Or in our notation, it is this: the support count of X as a fractions of the total number of transactions in the data set. That's called SX in the textbook, all right? But for our discussions, we'll stick with this notation. It's a little bit easier to remember. Okay, all right? So now let us illustrate these definitions using a sample data set. This is a toy example. Here we have 25 transactions and 6 items. All right, of course, in practice, you have a much bigger data set because every transactions here represent the items that are purchased by a customer, from a supermarket. So in practice, you do not have 25 transactions only. You may have 25 million transactions instead. And here in this toy example, we have 6 items, namely A, B, C, D, E, F. But of course, in practice, the supermarket sell much more than, many more than that, just 6 items. You could be selling like thousands of items. Right? But this is just a toy example for us to illustrate the various concepts and definitions. All right, now, so from this data set, let us take a look at some of the definitions or notations that we have. N, which is the numbers of transactions in the data set, is 25 because there are 25 transactions here, right? And I is the set of all items that are carried by the supermarket. So in this case here, we have 6 items, A, B, C, D, E, F. So this is the set of all items I. All right. Again, in practice, I could be much larger, right? And could be much bigger. Right? Now, the first transactions in the item in the data set is this one, and we are using what we call one-hot encoding. So we put a 1 at a particular entries in this kind of like table to indicate the presence of a certain item. So if you look at the first transaction, you see we have 3 ones under A, B, and F. And therefore, the first transactions, it's the item set ABF, okay? Transaction 20 is the item set ABCE. So let's take a look. This is transaction 20. We have A, B, C, and E here, right? Okay, and we say that this transaction 20 contains the item set ABE because ABE is a subset of the transactions, right? Sometimes we also say that transaction 20 supports the item set ABE. That is also commonly used as a terminology, okay? Now, if you consider the item set ABE, we can count the support of it from data set, and we find that the support count of ABE is 3. That is because among the 25 transactions in the example, we have transaction 4, 18, and 20 containing the item set ABE. For example, item set 20, transaction 20 is ABCE, it contains ABE, and therefore it is counted, all right? Transaction 18, which is here, is ABE as well, so it contains ABE, and therefore transaction 18 also support the item set ABE as well. So if you go through the whole data set, you'll find that there are 3 transactions in the data set, namely 4, 18, and 20 support ABE, and therefore the support count of ABE is 3, all right? And similarly, you can also, go through the whole data set, and you will find that the support count of the item set CD is equal to 9 because there are 9 transactions containing CD, okay? And CD, this item set, because it contains 2 items, therefore it is called a 2-item set, all right? ABE, on the other hand, it's called a 3-item set because it contains 3 items. So I hope that, with this example, you're more familiar with the terminology, with the notation. All right. Okay. Now, so what is our objective? Our objective is that you're given a transactional data set, such as this one, with a huge numbers of transactions, presumably with a large number of items. What we want to do is to be able to process this data set and to obtain what we call association rules. All right. And an association rule has the following form: X implies Y, where X and Y are some item sets. Okay. And the semantics, again, is that if the items that are mentioned in the item set X occurs in a transaction, then it is very likely that the items mentioned in the item set Y also occur in the same transaction. So that's the semantics of the association rule. And our objective, again, is to find out all those rules. All right. Now, there are 3 requirements for an association rule, such as X implies Y, to be valid, that should be reported, okay, to a manager, for example. So what are the 3 requirements? The first requirement is that X and Y have to be non-empty and disjoint. All right. Non-empty means that X is not empty set, Y is not empty sets. And they have to be disjoint, meaning that they do not overlap. So the intersection between X and Y has to be empty. There is no item that are mentioned in both X and Y. All right. So this is the first requirement. The second requirement is what we call the support conditions, which state that the support count of X union Y divided by N, which is the total number of transactions that you have in the data set, has to be not smaller than a threshold. Okay, here we use rho S to represent that threshold, and this is called the support threshold. Okay, and then the third requirement is called the confidence conditions, and it requires that the support count of X union Y divided by the support count of X to be not smaller than another threshold. Here we use rho C to represent that threshold. This is called the confidence threshold. So altogether, there are 3 requirements for a rule, X implies Y, to be considered a valid association rule that should be reported to the manager, right? That to be extracted. Okay. So again, the purpose of association rule analysis or mining, what the algorithm needs to do is to find out all those rules that satisfy these 3 requirements. All right. And what we're going to do next is to discuss how these rules could be found, all right, or could be computed. All right. But before that, let us spend a couple of minutes to further elaborate on these 2 conditions, namely the support conditions and also the confidence conditions. All right. So the support, well, if you look at the support condition requirements, we require that the support count of X union Y divided by N to be not smaller than rho S. And rho S, as I said, is called the support threshold. It is a threshold, it's a parameter that we set. All right. You can change it, make it larger or smaller, depends on your needs and applications. Now, the support condition here ensures that the mined rules concern items that occur in a good portions of the transactions. And so the rules that we discovered are of sufficient interest or importance to the analyst. So let us take a look at the requirements again, which essentially say that the support count of X union Y divided by N, it's larger than or equal to rho S. All right. So if you look at this ratio or this fractions, this can be interpreted as the fractions of the transactions in the data set that mentions all the items in the rule, which include the left-hand side and the right-hand side, right? As a fractions of the total numbers of transactions in the data set. Okay. So for example, if in your data set there are 1 million transactions, all right, and suppose you set rho S, the support threshold, to be, let's say, 1%, that means that any rules that satisfy the support requirement has to have a support count of at least 10,000, right? So this implies that there has to be at least 10,000 transactions in the data set that include all of the items mentioned in the rule X union Y. All right. So if you think about it, the reason why we have this support requirement or support conditions is that we want the rules to be about, the rules that we report to the manager to be about those items that are popular. All right. So if a association rule include items in X and Y whose support doesn't satisfy the support requirement, it means that those items are not being purchased very frequently. So those items are of lesser importance, to the business of the supermarket, and therefore we might not want to bother the manager with all those less important rules, and that's the reason why we have the support requirement. Okay, all right. So that's one condition, and the other conditions was the confidence conditions. This one is easier to understand. With the confidence conditions, which is here. Right, we have another threshold, rho C, and this is called the confidence threshold. And essentially what we require is that this ratio, right, which is shown here, has to be not too small, has to be at least equal to rho C, the confidence threshold. Now, how do we interpret this ratio? This essentially could be interpreted as the conditional probabilities of P Y given X. That is to say, if X occur in a transaction, that is, if the items mentioned in the item set X appear in a transactions, what is the conditional probability that those items mentioned in Y, which is the consequence of the rule, also occur in the same transactions? So this ratio here gives us the conditional probability. All right. And obviously we want this conditional probability to be high so that the implications, so that we are more confident in the implications, that the likelihood that the implications is true. All right. So the ratio here gives the conditional probability Py given X. That is to say, the item Y occurs, the item set Y occurs in the transactions given that item set X occurs in the same transactions. So the confidence conditions ensures that the mined rules are of high confidence. All right, so the support requirement ensures that the rules involve items that are important, that are popular, that are sold very frequently. The confidence requirement is about satisfying the confidence threshold of the rule. That means that we want the conditional probability to be high enough. So these are two different concepts. And that's why we have two different conditions and two different requirements for rules to be valid. Okay, so that's the support and confidence requirement. All right, now let us use our example data set here to illustrate the support and confidence requirement. All right, now let's say I set my support threshold to be 20%. Let's say I set the confidence threshold to be 65% or 0.65. Now, with respect to our toy example dataset D, let us consider the rule. F implies AB. Now, I said that with the general form of the rule looks like this, X implies Y, right? So here, X is equal to the item set F, and Y is the item set AB, right? So I want to check whether this rule is valid or not. So I want this rule to satisfy three requirements. The first one is quite straightforward. The left-hand side and the right-hand side should not be empty. That's satisfied. There should be no overlapping items between the left and the right-hand side. That's also satisfied. So the first requirement is good, right? What about the second requirement, which is a support requirement? So if you think about the support requirement, what we need to do is to obtain the support counts, all right? Support of X union Y. That is to say, in the data set D, how many transactions contains X union Y? X union Y is ABF, right? So if you look at the toy example data set and if you count, you'll find that there are 2 transactions in the whole data set that contains ABF. And therefore, the support count of ABF is 2. All right. So for the support requirement, we require that this to be not smaller than row S. So, and the numbers of transaction N is 25. And therefore, the support is 2 over 25. This is 8%. But in our example here, the support requirement is 20%. This is not satisfied. All right, so this rule does not satisfy the support requirement. Okay, now what about the confidence requirement? For the confidence requirement, we need to calculate this ratio. So we need two counts. One is the support count of X union Y, and the other is the support count of X. Support count of X union Y is already done. The support count of Y, which is, the support count of X, right, which is the support of F here. If you go through the data set, you'll find it to be 3 because there are 3 transactions containing the item set F. So in terms of the confidence requirement, we compute this ratio. That is 2/3, which is 67%. This exceeds the confidence requirement, and therefore this is good. All right. So for this example rule, F implies AB, we find that it satisfies the first requirement. It satisfies the confidence requirements as well, but it doesn't satisfy the support requirement. All right. And therefore, this rule should not be reported, should not be extracted. Okay. So this rule satisfies the confidence conditions, but not the support conditions. All right. So it's just an illustrations of the definitions of association rule. Okay. Now, before we move on to discuss about like how exactly do we find out this counts to determine whether this rule is valid or not, let me make a remark. In this toy example, I'm using a support threshold of 20% and a confidence threshold of 65%, right? In practice, the support threshold should be much smaller. All right, with my experience with finding associations or frequent patterns from different kind of data set, usually the support threshold would not be set as so high. For example, you may want to set it to 1% or 0.1%, depending on your applications. All right, 20% is way too high because 20% means that at least one out of 5 the transaction contain those stuff. You seldomly have specific items in your supermarket that is being purchased by more than 20% of the transactions, right? However, in this toy example, I have to set a fairly high support threshold. Otherwise, I will have to create a very large toy example data set in order to illustrate this idea, right? So, but the remark that I made was just to make sure that when you are applying association rule in your data sets, you don't set the support threshold to be such a high value, because Professor Kao showed an example with 20% support. That's not the usual case in practice. All right. As another remark, in this toy example, I set the confidence threshold to be 65%. This is usually too low, right? In practice, you want the confidence threshold to be much higher, perhaps 80%, perhaps 85%, because that is about how valid the rule is, how likely that you will see the right-hand side or the consequence, given that the antecedent occur, right? So you want that to be, more, higher value instead of like just 65%. So typically that would be higher, but again, for illustration purpose, I have to set it to be lower in order to illustrate this stuff. All right, okay, just a very a minor remark. Okay, right. So now we would like to see how exactly what would be the algorithm or the procedure for finding or discovering such association rules. Okay, now so here is how to find the rules exactly. The typical algorithm for mining this association rule would take 2 steps. In particular, the a priori algorithm that we'll mention shortly will take these 2 steps to discover all the rules. Now, the first step involves finding all the frequent item sets from the data sets. So what do we mean by frequent item sets? Well, a non-empty item set S is called a frequent item set, or is said to be frequent if its support count is not smaller than row S multiplied by N. Again, row S is the support threshold, N is the total number of transactions that you have in your data set. All right, and we call S a frequent item set this way. So the first step of association rule mining is to process your data sets to discover all such frequent item sets first. All right. Now note that all the valid rules must have all the items that are mentioned in the rule form a frequent item set. So what exactly do I mean? Well, think about it again. This is a typical form of association rule. And for the support conditions, we require that the support count of X union Y divided by N to be not smaller than the support threshold. This is a support requirement, right? So that means that the support count of X union Y has to be not smaller than rho S multiplied by N, okay? All right. So if you compare to the conditions there, or what you call a frequent item set here, you see that all valid rules, if I consider the left-hand side and the right-hand side of the rule combined together, that is X union Y, it forms a frequent item set. All right. So the reason why we want to figure out all the frequent item sets first is that we know that any rule that we're gonna report has to satisfy the support requirement. And so the items mentioned in the rule must form a frequent item set. So it makes sense to figure out all the frequent item sets first. So that's the first step of the algorithm, okay? Now, the second step of the algorithm is that after we have found out all the frequent item sets, then we'll try to derive rules from them, okay? So we generate rules from the frequent item set that we discover in the first step. In particular, for each frequent item set S that we found in step 1, we will partition the item set S into a left-hand side and a right-hand side, all right? So we partition S into two non-empty disjoint subset X and Y. So X is not empty, Y is not empty, X intersect Y is empty, and that the unions of them is S, all right? So the first requirement basically is to make the rule form satisfy the first requirements of the association rule. And this simply means that this is a partitioning of the frequent item set S. All right. So given a frequent item set, I want to partition it into the left-hand side and the right-hand side. All right. And that would form a candidate rule. All right. So now what we need to check is to check whether this rule satisfies the confidence condition. Oh, wait, for a rule like this, do we need to check its support conditions as well? Well, the support conditions should be already satisfied, right? Because X and Y's come from S, and S is a frequent item set. So we know that this rule must already satisfy the support condition, right? So the additional thing that we need to check is whether it satisfies the confidence conditions as well. That is to say, we need to check whether this ratio, the support count of X union Y divided by the support count of X, whether that is at least equal to rho C, the confidence conditions. All right. And if so, then this rule is valid, it's good, then we extract it, we collect it. All right. If not, then we discard it. Okay. And then we have to repeat the steps for all possible partitioning of the set S. And once that is done, we take another frequent item sets that we obtain from step 1 and we do all of these again. All right. So for all frequent item sets that we found in step 1, we consider all possible partitionings of S that satisfy these two bullets. All right. And those that satisfy these two bullets will be reported as valid association rule. So this is the general framework of how we discover association rule from the data sets. Okay. Now, of course, there are certain details that we still need to fill in, such as how do we achieve step 1 and how do we perform this check in step 2, right? So, but in general, step 2 is much easier. So let us talk about step 2 first, and then we'll go back to step 1 and talk about how exactly would be the algorithm that we use to extract those frequent items. Step 1 is more elaborate, right? Okay, so let's talk about step 2 first. Right? Now, again, I'm going to use a running example to illustrate. Here, let me set the support threshold to be 20% again. Again, in practice, you don't have such a big support threshold, but just for illustration purpose, let's say rho S is 20%. All right. So step one involves finding all the frequent item set X such that the support count of X is at least this value. All right. So in the toy example, you remember we have 25 transactions. And if I set the support threshold to be 20%, this means 5. All right. So any item set X is considered frequent if its support count is at least 5 in our toy example. All right. So if you go through D, if you go through this toy example data sets, all right, if you exhaustively enumerate all possible item sets and count the supports, you will figure that this table shows all of the frequent item set that you can find from the data set D. All right. So these are the only frequent item set that you'll be able to discover. Okay. So for example, you have A, B, C, D, E being frequent, A, B being frequent, and so on. Okay. Now, so how exactly do I compile this table? How exactly do I process the data set to obtain all these counts? This would be the details of step one that we will discover that we'll discuss later. Right. Now, for the moment, let's assume that we have some way of compiling this table. In particular, we have all these support counts of the frequent item set. Now, you notice that in our example here, our support threshold or support counts threshold is 5 supports. All right. And you notice that all of these support counts are at least 5. So they are all frequent. Okay. All right. So now, assuming that we have some way of compiling this table, and the next step is what? Well, it would be step number 2 here, which is about generating the rules. All right. So what do? We take a frequent item set, try to partition it into a left-hand side and a right-hand side, and then check the confidence condition. Right. Now, the first thing that we notice is that a frequent item set that contains only one item, or what we usually call singleton, right, does not generate any rule. Because if you have only one item in the frequent item set, you cannot partition it into a left-hand side and a right-hand side that are non-empty, right? So that means that for these frequent item set that consists of one item each, they do not derive any association rules, right? So we have to care about the others, right? Now, okay, but for the other frequent item sets, we have to derive rules and check the confidence conditions. As an example, if we consider the 3 item set CDE, which is here, this is frequent, all right? So what do we need to do for step 2? Well, we have to partition CDE into a left-hand side and a right-hand side, and then check the confidence conditions, right? So what are the possible partitioning of CDE into a left and a right-hand side? There are 6 candidate rules, okay? We could put C on the left-hand side, D on the right, or we could put CD on the left-hand side and E on the right, and so on, right? So we have 6 possible rules, okay? Now, and for each one of these rules, we have to check the confidence conditions. What do you mean by checking the confidence conditions? We have to compute X union, the support count of X union Y divided by the support count of X for each one of these rules, right, where X and Y are the left-hand side and the right-hand side of the rule. So let us take one of them as an example. Let's say this candidate root, all right? So we need to check its confidence conditions. And that means that we need to check the support counts of X union Y, which is CDE, right? Divided by the support count of the left-hand side, which is C, right? So now the question is, do we have these support counts? Well, the answer is yes, we do have these support counts. They can be found in this table. So what is the support count of CD? Do we have it? Yes, we do. This is 5, right? Do we have the support count of C? Yes, we do, here, right? It's 11, okay? And so by looking them up, we'll be able to determine that the confidence of this rule is 5/11, which is 45%. All right, and so on. So we check the confidence of all of these 6 rules that we derived from the frequent item set CDE. All right, and then we repeat this process for the other frequent item sets. Partition it into 11 on the right-hand side, check the confidence, etc. All right. Now, a while ago, I mentioned that we could compute the confidence of this rule by checking these 2 support counts. And we said that these support counts are available in this table, right? Actually, we can show that the support counts are guaranteed to be available. That is to say, if I have compiled this table, which consists of all the frequent item set and the support counts, then checking the confidence later in step 2 is just simply a lookup. We can show that all of these counts are there, all right, for us to look up and to compute. I'll talk about that. I'll explain that shortly. Now, coming back to our example here. So, for example, like if we set the confidence threshold to be 65%, then if you look at all these 6 rules, we find that this rule and this rule, right, these 2 satisfy the confidence requirement. But for the other 4 rules, the confidence of them are not strong enough. All right. And so among the 6 rules, only these 2 rules are valid and should be reported, should be collected. The other 4 rules should be discarded. All right. Okay. So if you repeat this process for all of the frequent item sets that we found in step 1, and for each one of them, do the partitioning, derive all the candidate rules, check the candidate rules confidence, and eventually what you will get is this results. Right? So this table shows all the frequent item. So this table shows all the valid association rules that we could discover from our data sets. So here we have 10 of them. Okay? And we show the, and we show the confidence values of all of these rules. Right? So they all exceed the 65% threshold. All right. Okay. Now, so again, let's take a look of step 2 again, which is to generate all the candidate rules from a given frequent item set, check the confidence to see which one of them satisfy the confidence requirement. So this step 2, generating rules with sufficient confidence from frequent item set is, in my opinion, relatively straightforward, right? I've already illustrated how this is done. Okay, giving, let's say, 1 frequent item set, I derive all the candidate rule, check the confidence. So it's quite straightforward, right? So the question is it computationally expensive? Well, we notice that a frequent k item set derive 2 to the power k minus 2 possible candidate rules. For example, here we have this frequent item set CDE. This is a 3 item set, right? So k equal to 3. All right. So how many rules do we derive from it? The answer is 2 to the power 3 minus 2, which is 6 rules, right? So in general, if you give me a frequent item set that is a k item set, which means that it contains k items, there are 2 to the power k minus 2 possible rules that we have to check the confidence, right? Why 2 to the power k minus 2? Well, for each item, you could either put it in the left-hand side or in the right-hand side. So that's why we have the 2, right? Because we have k items, the possible combination will be 2 to the power k. But 2 of those combinations are invalid. Namely, when you put all the items in the left-hand side, leaving the right-hand side empty, or you put all the items in the right-hand side, leaving the left-hand side empty, these 2 cases should be discarded because we require that x and y cannot be empty, right? So that's why we have this minus 2 here, right? So, but anyway, given the k item sets, there are 2 to the power k minus 2 possible rules that you have to check. Now, in practice, the values of k is not very large, right? For example, if you apply association rule mining on, let's say, a real supermarket data sets, well, we have some experiences in doing that in some real data. What we found was that most of the frequent items that we found consist of mostly 2 to 4 items. all right? So there are some frequent items that are bigger, which consists of 6 or 7 or even 8 items, but those are relatively rare. Most of the item set that we discover, from some typical data set, usually consists of like 2 to 4 items only, all right? So for example, if a frequent item set consists of 3 items, in our discussions, we know that there are 2 to the power 3 minus 2 equal to 6 candidate rows that we have to check, right? If k is equal to 4, if I have a frequent item set with 4 items, the candidate items, the candidate rows that I have to check would be something like that, which is 62, right? So, well, all of these values are relatively small, all right? It is very easy for a modern day computer to check all the, the ratio, the confidence of this rule without much problem. Even though there could be quite a numbers of frequent item sets, but generally this part is manageable. Deriving the rules and checking the confidence of the rules, these are computationally feasible. All right, so step 2 generally is not a big problem for association rule analysis. All right. Now checking the confidence of these rules is easy, provided that the support counts of all the subsets of the frequent item sets are available. Because what it means is that if you want to check the confidence of all of these derived rules, you need the support count of many subsets of CDE, right? For example, if I need to, if I want to check, let's say this rule, all right? What about, if I want to check, let's say this rule, what do I need? Well, I need the support count of CDE divided by the support count of CD, right? Do we have this count? Yes. The support count of CD is here. The support count of CE is here. All right. So if this is what we obtain from step number 1, then step number 2 is just a lookup to compute those ratios, as I mentioned. All right. So one thing that you notice is that suppose you are given a frequent item set CDE, right? In order for you to derive the possible rules and to check the confidence, essentially what you need is the support count of any subset of CDE. For example, the support count of CD, the support count of DE, the support count of C, etc., etc. And if you look at this table, an interesting thing that you find is that if CDE is a frequent item set as listed in this table, so are all the subset of CDE, right? Any subset of CDE, let's say CD is here, let's say CE is here, let's say D is here. So that's why all of the support counts are already available, right? If you have compiled this table of all the frequent item sets. So basically what I'm trying to say is that for step number 2, checking the confidence of the rules means checking a whole bunch of those ratios. The support counts that you need to compute all those ratios are readily available, right? So there's really not much of a problem in achieving or completing step 2. And as I said, since K, the size of the frequent item sets is usually very small, right, for typical applications. And therefore, an exhaustive approach for generating and checking the rules, just like what I did, right, is usually not a problem at all. It's not a big computational problem, okay? However, step number 1 is much, much more expensive. So what is step number 1? Step number 1 is, given the data set D, try to find out all the frequent item sets and the support count. Now that step turns out to be extremely expensive, all right? So let's see why is it so expensive, okay? Now, if there are M different items in a data set, there are essentially 2 to the power M minus 1 possible non-empty item sets. Now, the reason why this computational problem is so much more expensive than step 2 is that even though, if you look at the cost, this is 2 to the power M minus 1 possible item set. Each one of them could be frequent. Previously, there are 2 to the power K minus 2 possible rules for you to check. The difference is that this K is usually fairly small, right? As I said, the size of a frequent item is usually not very big. However, this M here refers to the total numbers of items in your data set. So if a supermarket carry 10,000 items, then there are these many possible item sets. Each one of them could be a frequent item set. So if you take a very straightforward approach, that is, you simply do a brute force method of enumerating all possible subsets of the items, and then check the support counts to see whether they're frequent or not. This is impractical because this number is simply too huge, right? This is actually, I don't know how big it is, but to the power 64 is already trillions and trillions and trillions of things, right? So that's a very, very large number, okay? So this is impossible. It is impossible for us to enumerate all of the possible item sets and check the support count to see which one is frequent or not, all right? Now, so checking which item sets are frequent and finding the support using a brute force approach is impractical because there are so many possible item sets for us to check. Now, a while ago, I said that, well, in most cases, the frequent item sets usually have fairly small numbers of items. So if I want to make step number 1 faster, I don't really need to check all of these items, right? Maybe all of these item sets, right? Maybe what happens if I restrict my search space to considering only those item sets that have, let's say, 6 or fewer items, assuming that any item sets of 7 or more items cannot be frequent because it's not very likely, you know. So, but still, that is very expensive because the numbers of item sets that you can derive, even if you limit the size of the item sets to be 6 or fewer, you are talking about this many possible candidates. Right? And this worked out to be something like 10 to the power 21, right? So this is still an extremely huge number. So even if we restrict the size of the item set to be a small number, still we have so many possible item sets, and there's no way for us to exhaustively enumerate them and check the support to see which one is frequent or not. All right? So we need to do something smarter. Now, the a priori algorithm basically is the algorithm that can help us discover this kind of what we call frequent patterns or frequent item sets in a more practical, as a more practical solutions. So as I said, let's say you have M items in your supermarket that are carried by the supermarket. There are to the power M minus 1 possible non-empty candidate item sets, and for which you might need to check the supports to see whether they are frequent or not. Now, we can arrange these item sets in what we call a lattice structure. So here is an example. In this example here, we have M equal to 5. That is the total numbers of different items that we have in the data set being 5, namely A, B, C, D, E, only 5 items, all right? And there are 2 to the power 5 minus 1 or equal to 31 non-empty sets. And these are illustrated in this lattice, okay? And in this lattice, we also have some edges connecting some of the item sets. Each one of these edges represent a subset relation, all right? So for example, we have an edge that goes from ABCD to ABC because ABC is a subset of ABCD. We also have this edge, ABD being a subset of ABCD. We also have this edge because ACD is also a subset of ABCD. So essentially, each edge here represents a subset relation. And based on this, we can arrange this the set of all possible item sets into a what we call a lattice structure. Okay, so the a priori algorithm was proposed, interestingly, independently by 2 research groups. All right, and these are the leaders of the 2 groups. All right, and they you know, the algorithm that they derived, they proposed, is based on what we call the a priori property. And the a priori property says that if X is a frequent item set, then any non-empty subset of X has to be frequent as well. All right. So here's an example. Let us consider data set D. Previously, we mentioned that the item set CDE is a frequent item set. That is to say, the support counts of CDE reaches a certain level. And in our toy example, the threshold is 5, a count of 5, right? So it means that the support count of CDE has to be at least 5. And in our example here, we have the support count of CDE being exactly 5. Okay. All right. Now, the a priori property says that if X is frequent, then any non-empty subset of X is also frequent. So here in this example, we have CDE being a frequent item set. We notice that all of the non-empty subset of CDE are also frequent in D. That is to say, if you look at this frequent item set table, right, CDE is found to be frequent, and that's why it is listed in this table. You'll notice that all of its subsets, for example, C, for example, E, for example, CE is here, etc., all of these subsets are also frequent. That's based on the a priori property. All right, so one more time. If an item set X is frequent, then any non-empty subset of X has to be frequent as well. So this is a priori property. All right. So how do we use this a priori property to help us compute the to help us discover the frequent item sets more efficiently? So this is again showing that if CD is frequent, all of its subsets are also frequent as well. All right, just to illustrate the a priori property. Now, in fact, so from the a priori property, what we can derive next? Well, first of all, let me show you, give you a very simple proof that the a priori property is true, right? So if X is a frequent item set, any non-empty subset of X has to be frequent. So here's the proof. Let me use support X to represent the support count of X. So this, by definition, is the number of transactions in D that contains the item set X, right? And let us consider any subset Y of X. And if a transaction T in the data set contains X or support X, which is illustrated here, it means that X is a subset of T. All of the items mentioned in X is also there in the transaction T. And that's why X is a subset of T here, right? But since Y is a subset of X and X is a subset of T, it means that Y has to be a subset of T as well, right? So it's illustrated here. Y is a subset of T. And therefore, the transaction T contains Y or support Y as well. So from here, what we are saying is that if a transaction support X, the same transaction must support Y as well. All right? And therefore, the support count of Y cannot be smaller than the support count of X, because any transaction supporting X has to support Y. So the support count of Y cannot be smaller than the support count of X, right? And because X is a frequent item set, it means that the support count of X is not smaller than this value, than the threshold. And as we said that the support count of Y has to be not smaller than the support count of X, and therefore the support count of Y must not be smaller than this value as well. And therefore, Y is also a frequent item set, right? And that proves the a priori property. So any item set X, if it's frequent, then any subset of X, let's say Y, has to be frequent as well, okay? So the conversely, if an item set X is not frequent, suppose I give you an item set and say this is not frequent, all right? Then if we consider any superset of X, let me call that Z, all right? This cannot be frequent either, right? Because if Z is frequent, by the a priori property, X has to be frequent as well, and that will lead to a contradiction, right? So if you give me an item set X, if I know that this is not frequent, then any superset of X cannot be frequent either, right? And this probably actually help us determine the frequent item set, more practically. Therefore, if we know that an item set is not frequent, we do not need to check any superset of X and find its support when we're trying to discover the frequent item sets. So the a priori algorithm makes use of the a priori property to prune the large numbers of item sets to a manageable number. For example, suppose we found that, while we are processing the data set, suppose we found that the item sets charcoal is not frequent. Let's say, assuming that not a lot of people going to the supermarket to buy charcoal, but the supermarket does carry charcoal, all right? So if we find that charcoal is not a frequent item set, then any other item sets that contain charcoal cannot be frequent either. For example, charcoal milk, this item set cannot be frequent. And so we do not need to consider this frequent item sets when we encounter support in order to determine the set of all frequent item sets. So that saves us a lot of work, all right? So here is an illustration. So again, the idea of a priori or the a priori algorithms is that given this lattice of all possible item sets, intuitively what the algorithm needs to do is to explore this lattice, considering every item set, check the support count to see whether they're frequent or not. That's intuitively what we need to do, right? But a priori want to make this more efficient by applying the a priori property. So while exploring this lattice of item sets, the a priori algorithm would try to explore it level-wise, all right? So it starts with those small item sets. Let's say the size 1 item set. Next, it would explore the slightly larger item sets, namely the size 2 item sets, and so on. And at some point, if the a priori algorithm finds that a particular item set, let's say AB, is not frequent, then the algorithm knows that any superset of AB cannot be frequent either. So in the following exploration, the algorithm would avoid counting the support of this whole chunk of item sets, because that's not necessary, right? And that is essentially the idea of a priori of how it, given this lattice, which is extremely large. So it used the a priori to prune away a big chunk of the, of this lattice. And the effect is that basically most of the item set in this lattice can be pruned. And so the item set that really need to be counted for their support would be reduced to a much more manageable collections, right? So that is what makes the a priori algorithm practical, okay? So here, let us get into some more details of the a priori algorithm. It is an iterative algorithm. Here, let me use the notation Li to denote the set of all frequent item sets, all right? So an item set is in Li if it has I items in it, and that it is frequent, okay? Now, as I said, the a priori algorithm is iterative. So let's take a look at what we do or what it does in each iteration. Now, in the first iteration, the a priori algorithm will scan the data sets one time, right, to find out all the frequent 1 item set. Again, these are also called the frequent singletons, right? Okay, to see which items are frequent. And all of these frequent items will be put into the set L1. This is the set of all size 1 frequent item sets, okay? And in the second iterations, the a priori algorithm would generate a candidate set called C2, right, based on the contents of L1. In particular, an item set X is collected in this candidate set C2 if X contains 2 items, that is, it's a 2 item sets, and that all of its size 1 subsets are frequent in L1, okay? And after C2 is prepared, then the data set will be scanned one more time to check which item set in C2 are frequent. Those that are frequent will be put into the set L2. This is the set of all frequent 2 item sets, all right? And so on, okay? And in general, during the ith iterations, the a priori algorithm would construct a candidate set Ci, and an item set X is put into this candidate set Ci if it contains I items, and that all of its size I minus 1 subsets are frequent. That is, all I minus 1 subset of X are frequent in Li minus 1. Okay. And once this candidate set Ci is prepared, the a priori algorithm will scan the data set one more time to see which item set in Ci are actually frequent. Those that are frequent will be put into Li, the set of all frequent I item sets. Okay. And the a priori algorithm will terminate when, during an iterations, the candidate set generated, namely Ci, is an empty set, then it terminates. All right. And the set of all frequent item sets is the unions of all the Li's that were discovered throughout all the iterations. And basically that's the structure. All right. So let us illustrate the a priori algorithm using our toy example again. Okay. So in the first iteration, what a priori does is, first of all, it will prepare the candidate set C1. Right. In our toy example, there are 6 items carried by the supermarket, namely A, B, C, D, E. Each one of them form a 1 item set. All right. So C1 looks like this. Okay. And we prepare 6 counts, 1 for each size 1 item set. And then we scan the database to find out the support counts of each one of them. All right. So when we process the first transactions, we find it contains A, B, and F, right? So we do some subset testing. We find that it contains the set A, the set B, and the set F, all right? And therefore, we increment these 3 counts by 1, okay? Next, we process the second transactions. We find it contains C, D, and E, and therefore, the support count of these 3 item sets are also incremented by 1 each. And this is the result, all right? Now, after you process all the 25 transactions and count the support, you will get this as a result, okay? These are the resulting support counts, all right? Now, suppose I assume that we have a support threshold equal to 20%. Then 25 transactions multiplied by 20% means 5 counts. So the support threshold is 5 support counts. And if you look at these 6 candidates, you'll find that A, B, C, D, E satisfy the support requirement. F, however, is not frequent. All right. So we collect A, B, C, D, E into L1. This is a set of all size 1 frequent item set. Now, once L1 is collected, what a priori algorithm does is that it would prepare C2. Right? And C2 is obtained by what we call joining the item sets in L1. So effectively, what we're doing is that we take 2 item sets from L1, join them together to form a candidate in C2. All right. So because L1 consists of A, B, C, D, E, C2 consists of these 10 size 2 item sets. All right. So we prepare 10 counts and we repeat the process, namely scan the database to compute the support counts of these item sets. And the first transactions contain A, B, and F, right? So it contains A, B, and therefore this support count is incremented by 1. Now, what about BF? Well, BF is not in C2 because F is not frequent. So we do not have to care about the support count of BF, for example. All right. So if you process all of the transactions in the data sets, you will collect all of these support counts. All right. And again, the support threshold is 5 units. And therefore, we notice that A, B, BC, BD, etc. These are frequent. And also AC, AD, and AE are infrequent, are not frequent. So we collect the frequent size 2 item set into L2. And now we repeat the process. From L2, we create a C3, scan the data sets to obtain L3, and so on. All right, so this is the structures of the a priori algorithm. Now, in general, from during the ith iterations, what the a priori algorithm does is that it will have to prepare a Ci from Li minus 1. And this is the general process. So the a priori algorithm uses the functions called a priori gen to generate Ci given Li minus 1. Now, in notations, we write this. We call this kind of like a joined operation. We take Li minus 1, do a self-join to obtain Ci, all right? Now, the details of this operations is here. This is called the a priori gen function. So what a priori gen does is that it considers all pairs of I minus 1 item set X and Y from Li minus 1 that share I minus 2 common items, all right? That is to say, I take an X and a Y from Li minus 1. Let's say this is X. Let's say this is X. Let's say this is Y. All right. Each one of them comes from Li minus 1. Therefore, X has I minus 1 items. Y also has I minus 1 items. All right. Now, we take this pair if they share I minus 2 common items. That is, they overlap with I minus 2 items. And so this is the part that they overlap, and it consists of I minus 2 items. So we have one extra item from X that is not in Y. We have one extra item. We have one extra items in Y that is not in X. So if we combine X and Y together, you get I items, right? So here we have I minus 2 plus 1 here plus 1 here. So we have I items. So union, if the union of X and Y is an I item set. All right. So and then we will scan the database to check its support. So to generate C3 from L2, for example, we need an XY pair from L2 that share one common item. For example, BC and CD are found in L2. Okay, in L2 we have BC here, all right, and CD here. Both of them are frequent, so they are from L2. And we join them together, getting the union of it, and that would give me BCD, right? This is one candidate, okay? However, before we put BCD into the candidate set C3, we have to do some more checking. Now, for each item set Z generated by joining, we will check to see whether all of its size I minus 1 subsets are in Li minus 1. And if so, Z is put into Ci. As I said, we write this to represent the a priori gen procedure. And here are a couple of examples. BD and CD are from L2. And they overlap by one item. So joining them, we get BCD. All right. Before we put it into C3, we check whether all of its size 2 subsets are frequent or not. All right. And we found that BC, CD, BD, these are all the 3 possible size 2 subsets of BCD. They are all frequent. They are all in L2. And therefore, BCD is put into the candidate set C3. As another example, let us consider AB and BC. Both of them are from L2 as well. All right, so we can consider joining them. If we join them, we get ABC as a 3-item set. But before we put it into C3, we have to check whether all of its subsets are frequent or not. Well, that's not the case for ABC because the subset AC is not in L2. If you look at this, AC is infrequent. All right, and therefore, if AC is infrequent, ABC cannot be frequent either. And therefore, ABC is not put into the candidate set C3. So we do not need to count the support of ABC in the next round, all right? So if you follow this procedure, you'll find that C3 will look something like this. That would be 4 candidate size 3 item sets. We scan the database to obtain the support counts. Those that are frequent will be collected into L3, all right? And from L3, this is what we get. We will have to create C4, all right? That is to say, we'll take two item sets from L3, join them together to get a four item set, and check whether the 4 item sets satisfy the requirement. So the only 4 item set that we can ever generate, whatever pairs of item sets that we get from C3, it will be BCDE. All right, whichever pair that you pick to join, you only get BCDE. Now we notice that one of the subsets BCE of BCDE is not frequent, and therefore BCDE cannot be frequent either, and so BCDE will not be put into C4, and as a result, C4 is empty, and therefore at this point, a priori terminates because there's no more frequent item set that can be found. All right, and so C4 is empty, L4 must be empty, a priori terminates. Now notice that in this toy example, we have 6 items. So previously we said that there are 2 to the power 6 minus 1, or 63 possible item set that we have to check the frequency, right? However, with the a priori algorithm in this process, how many item sets whose support are counted? Well, for size 4, there are 4. For size 3, there are 10. So altogether 14. For size 1, there are 6. So altogether 20, right? So altogether, the a priori algorithm has counted only the support of 20 item set instead of 63. So there is some saving. Because this is a toy example, the total number of item sets that we prune away without counting the support is not so dramatic. But in practice, we'll be pruning all, very big portions, or the majority of the item sets are being pruned. That doesn't need to be that don't need to be counted, right? So that's basically the a priori algorithm. And if you want to look at the pseudocode, the next 2 slides show the pseudocode of the a priori algorithm. You do not need to remember this pseudocode. All right, we will not ask you in the final exam to recite this. This doesn't make sense. However, we might give you some small example for you to derive some of the rules, check the frequencies of certain item sets in the examinations. So I guess I will have to stop here. Let's take a 3 minutes break, and after the break, we will have the midterm exam.